All right, 12.3, probability with counting permutations, combinations. Here's the deal. The number one thing you need to remember is that with probability, we're still always counting the number of successes over the total number of outcomes, which is the number of successes plus the number of failures. But I want you to just kind of think of it as a total, and I'll show you what I mean here in a little bit. Right? So that's what we mean by favorable outcomes over total possible outcomes. So just like we learned with combinations, permutations, you might need to think about how you can count up all the favorable outcomes and the total possible outcomes. You'll see some problems where they're talking about arranging groups. When they ask about arranging groups and order doesn't matter, you're primarily going to use this basic formula where you're going to do a choose, basically count all the ways to be successful over all the counting all the ways to have any possible outcome. So this is generally your formula for any type of arranging of a group. And then later down here, what if they're arranging a group in a specific order? It's probably going to be this. We could also say like maybe it's a permutation on the top, but usually there is only one specific order. And so we just put a 1 over all the ways to arrange in any number of order, right? So this is the one specific way to arrange it, and then this would be all the ways that you could arrange in different orders. But that kind of probably doesn't make much sense without some examples. So let's look at some specific examples to help us understand what we're talking about here. So example 1. Let's say that you claim you can read minds. So you let your friend pick 3 cards from a standard deck of cards. To test your ability, you will attempt to say the 3 cards that your friend picked without looking at them. Assume that you really do not have any special powers and are really just randomly guessing. What's the probability of you correctly identifying the 3 cards in any order? So that right there, in any order, that tells me order does not matter, and therefore we're talking about combinations. So on top, this is where we're going to use this basic equation. It's just going to be a combination over a combination, but let me show you what I mean. On top, we want all the ways that we could pick 3 cards out of the 3 cards that are correct, right? This is a success. Well, if there's 3 correct cards, and I'm choosing 3, the number of ways to pick 3 cards out of 3 that are correct is 3 choose 3. And you could plug that in your calculator, but anytime you're doing something choose itself, it's always just going to be 1. All right, so there's one way that you could pick these 3 cards that are correct out of the 3 cards that are correct. That's it. But on the bottom, you need to think of all the ways that you could pick 3 cards, including all the ways to be wrong. Well, how many cards are there in a deck? There's 52 cards, and you're choosing 3 of them. 52 choose 3 is 22,100. So there's your probability that you would get this right. It's 1 out of 22,100. Seems pretty unlikely. So if you really could guess those 3, maybe you do have some special abilities. Example 2 is another example here using these probability formulas. However, now we're going to see that order might matter. And I'm going to show you 2 ways that we could think about this problem. So let's read this one. It says a 4-digit passcode to enter a safe is made up of numbers 0 through 9. All right. And repeated digits aren't allowed. So if you use 9 in one spot, you can't use it again. If someone was to randomly guess the passcode, what is the probability that they guess the correct sequence? All right, so this is a permutation because this is correct sequence, right? So order matters, right? So if the passcode was 1, 2, 3, 4, and I typed in 4, 3, 2, 1, that wouldn't work, right? Because the order matters. So if order matters, we're talking about permutations. So let's think about that in permutations. Well, there's only one correct way to put in the passcode, right? Whatever it is, 1, 2, 3, 4, 4, 5, 6, 7, 8, whatever the passcode is, there's only one correct way to do it. But on the bottom, we need to think of all the ways that we could put in the passcode incorrectly and correctly. All the ways we could put in a passcode of 4 digits. Well, we have 10 numbers to choose from because remember, I start counting at 0, then 1 through 9. And I'm doing a permutation now because order matters, and I have 4 spots to put them in. So it'd be 1 over 10 permutation 4. That would be how I could figure this one out. Well, 10 permutation 4 is 5,040. So you'd have a 1 over 5,040 chance. That would be the answer. Now, I want to show you another way that you could think about this. This is often the way that I like to think about it. I think it just makes more sense to me than using the formula, but I like to show you the formula just so you know where it comes from. What I like to think of is, okay, you got 4 spots. 1, 2, 3, 4. And let's do this one at a time. What is the probability of the first number you pick being correct? Well, obviously there's one number in that spot that's correct out of 10 possibilities. But I don't want just one thing correct. I want all 4 of these correct. So I need this and this and this and this. Whenever we do and in probability, we multiply. If you see the word and, you're going to be multiplying. If you see the word or, you're going to be adding. But we'll talk more about that later. So I have 1/10 times, what's the probability of the next one being correct? Well, if I already used one of those and I cannot, repeated digits aren't allowed, now there's 9 possibilities. And then there would be 8, and then there would be 7. And so if I did 1 times 1 times 1 times 1, I get 1. And if I did 10 times 9 times 8 times 7, I get 5,040. And so we could do it either way and we'll get the same answer. All right, now we got this other formula here. This is called probability with combinatorics, but more specific, I wrote down it's called like multiple events with only 2 outcomes. And I think a better way to describe it would actually be repeated events. So if you're doing the same thing over and over and over again and you want to know like how many times you get A versus B, for example, like let's say flipping a coin over and over and over again and you want to get heads 4 out of the 10 times that you flip a coin, or rolling a dice and you want to see how many times you get the number 6 out of, 12 times of rolling the dice, whatever the situation may be, repeated events. And it's not just flipping coins and rolling dice. There's a lot of applications for this, but we're really talking about a repeated event where the probability doesn't change. We're just doing the same action over and over again with the same probability over and over again. And we can count, having 3 successes out of 5 and so on. I'll give you a couple examples of what we mean, but remember that. Repeated events. That's what we're using this thing for. And what does all this mean? Okay, well, S is your number of successes, and F is your number of failures. P of S, that means probability of success. So you have to figure out what's the probability of success in one situation. They'll usually give you that. And therefore, what's your probability of failure? Well, think of it this way. If your probability of success is like 1 out of 10, then failing must be 9 out of 10, right? Because your probabilities have to add up to 1. Or if your probability of success is 1/2, probability of failing is 1/2. So these two probabilities will always add up to 1. And this number of successes and number of failures, S and F, will always add up to this number right here, because that's your total number of attempts. Let me give you an example. Find the probability of flipping a coin 3 times. Okay, so we're going to do 3 total events. Success plus failure has to be 3. And getting heads exactly twice. Okay, so getting heads, that's a success. And I want it to happen twice. So that means I want my S to be 2. So let's see if we can figure this out. Well, I already know that my total number of events is going to be 3. Choose my number of successes to be 2. There's the first part of the formula. Now, the next part is the probability of success. Well, this sounds pretty easy. What's the probability of getting heads when you flip a coin? Well, it's 1/2. And how many times do I want that to happen? That's what this number is. How many successes do I want to happen? It's 2. And then the probability of failure will also be 1/2, right? So if I succeed half the time, I'm going to fail half the time. And since I'm succeeding, I want to succeed twice out of 3, that means I must fail 1 time out of the 3. Well, there's the formula. Now I just plug this all in my calculator. I'm good to go. You could plug this all in. You'll get a decimal, but this one's actually pretty easy to calculate. So 3 choose 2 is just 3. And what you can do when these are exactly the same, you can just add these exponents. So really this is just 1/2 to the 3rd power. And 1 to the 3rd power is just 1, right? But I'm going to do 1 times this 3 out here. So I end up with a 3 on top. And 2 to the 3rd power is 8. So the answer here is 3 out of 8. Again, you could plug this all in your calculator and get a decimal, but sometimes you don't need to do that. It's not that hard to calculate. Okay. what I want you to do is to do practice 3 on your own, but I'm going to try to help you set it up because we know where all the pieces go, but I want to make sure you clearly know what a success and failure is in this situation. So this one says, find the probability of flipping a coin 5 times. All right, so your total amount, success plus failures, is 5. Choose. And getting tails exactly 3 times. So success now in this one, success is getting tails. And we want that to happen 3 times. So this is going to be 5, choose 3. All right, you should know the probability of getting tails and the probability of getting heads. And so this is going to be a 3. So I think you could fill this out, and this part out, and then you can work it out from there. So go ahead and give that a try, and then check back when you're ready to check your answer. Okay, hopefully you saw that the probability of success is just still flipping a coin, so it's still 1/2, and the probability of failure is also 1/2. And if you're going to succeed 3 times, you must fail 2 because we have a total number of 5 attempts. 5 choose 3 is 10. You could do that in your calculator, or you could use Pascal's. You get a 10. 1/2 to the third times 1/2 to the second. Well, these are exactly the same, so you could just add exponents. That's like saying 1/2 to the fifth. 1 to the fifth is just 1. So 1 times 10 is 10. But 2 to the fifth is 32, so that's where that comes from. And then you could reduce this by 2 and get 5 out of 16. So the answer here is 5 out of 16. All right, we'll play with some more problems like this in class, but I thought you should see some good examples of those. And here, after seeing some different kinds of problems, what do you think are some key differences you should look for between combinatoric probability questions and permutation probability questions? So this was one way of doing combinatorics. This is, remember, repeated events. And then we gave some examples of combinatorics and permutations on the last page. So think about what the difference of those two are. All right, see you guys in the next video.